This is AS2 June 2015 and we're going to be looking at question 12b. So this question is a molar enthalpy question, and we are used to doing these sorts of questions with combustion data, so maybe burning a fuel like butane or something and working out the molar enthalpy of combustion of that reaction. To balance that you would need a 4 here, a 5 here, and 13 over 2 oxygens. But this reaction is actually a bromination, the addition of bromine to an alkene, and the previous parts in question 12 talk about that reaction. But essentially you're taking a double bond, part of hexane, and I will not draw the whole chain, and you're adding bromine dissolved in this solvent called TCE, and you're getting your addition product, your dibromoalkane, with the carbon-carbon bond now saturated, and just a single bond between your two carbon atoms. So we do it in exactly the same way as any other of these questions, and that is start with your delta H equals MC delta T, and then divide by the number of moles of, and in combustion data it's usually your fuel, divide by the number of moles of the fuel, but this time it's going to be the number of moles of our hexane, the organic product that is having bromine added to it. Okay, so that's what's happening in this reaction. You've got bromine dissolved in TCE, and then we're reacting it with a certain amount of hexane and seeing what the molar enthalpy of bromination is. What is the molar enthalpy change during this reaction? So this is what you need to remember. This is a two-step process, very simply. Now there's a lot of values given in these questions, and that's the hard part, deciding what values to use, but it's really just a two-step process. Do your delta H equals MC delta T, and then divide by your number of moles. How the question might throw you off is that the very first question asks you to work out the mass of hexane. We will need it later on, so we'll calculate it as the question asks, but it's not really the first part of our calculation. So it asks us to calculate the mass of hexane if the density is 0.6 grams per centimetres cubed. Well, you need to know your equation, that density is mass over volume. Rearrange that equation and you get that mass equals density times the volume. If your density is 0.68 grams per centimetre cubed and your volume is 2.0 centimetres cubed, you can notice that your units of centimetres to the -3 and centimetres to the 3 cancel each other out, and so you're left with the units of just mass, grams, and that's a good way to check that you've got your equation the right way around, if you get the correct units out. And so that gives us a mass of 1.36 grams. Okay, but we don't really use that at this stage, so it comes back into play later on, but we don't use that just at the minute. Next part is the rise in temperature, and so what we're working towards is getting our delta T value, and you could even write that in at this stage to remind you to use it in your equation later. So delta T is going to be your final temperature, which is 32.1, minus your initial temperature, which is 24.9, and that works out as 7.2 degrees centigrade. Okay, the next part is the mass of 100 centimetres cubed of TCE. Remember, that's your solvent. And this is going to end up as the mass of your solution. So again, we're working out mass. Up in the equation above, we worked out that mass is density times volume. And so that's going to equal your density, which is 1.33 grams per centimetre cubed, and 100 centimetres cubed is your volume. Again, you need to check that your volumes are in the correct, or in the same units, your density in grams per centimetre cubed and your volume in centimetres cubed. If one of them was in decimeters cubed, you would have to change them so they're both in the same units. Again, those units cancel out, and so you're left with a mass of 133 grams. Next question is the heat energy received by the 100 centimeters cubed of TCE. And this is where we use our delta H equals MC delta T equation. But again, we're normally used to using it with water. So the mass of water that is used to be heated up by the fuel that's being burnt, the specific heat capacity of water, and the temperature change of the water. But we are changing all of those those water values for TCE. So if you notice up here when we worked out the temperature change, it was the temperature change of the TCE. We are now being given the specific heat capacity of TCE. And in the question above, we worked out the mass of TCE. So in our delta H equals MC delta T, all of these values are for TCE. So yesterday we said that you always use it for water, but here our solution is TCE rather than water. You just need to make sure that the mass you're using is of all the same thing. So the mass is of the same thing, the specific heat capacities of the same thing, the change in temperatures of the same thing. You can't mix and match them. That's why we don't use the mass as the thing we worked out in the first question, which was the hexane, because that would be the mass of hexane times by the specific heat capacity of TCE, which wouldn't make sense. So it's the mass of TCE, which is 133, times the specific heat capacity of TCE, which is 1.30 joules per degree Celsius per gram, and times by the temperature change, which we worked out in the second part, which was 7.2. That works out as 1,245 joules. That's what I would write as your answer, but you could keep your number as more accurate than that for the rest of your working out. Next part of the question asks you for your molar mass of hexane. Don't let that throw you off. That's essentially just the RFM in grams, because the definition of molar mass is the mass of 1 mole of a substance, which is what the RFM is. So we're just working out the RFM of hexane. Hexane is going to be C6H12 because it's an alkene. So that's going to be 12 times your 6 carbons. And 1 is your mass of hydrogen, and you have 12 of them. So just adding those together, and you should get 84 grams. You need your unit of grams there, because it asks for molar mass as opposed to the RFM. The number of moles of hexane in 2 centimeters cubed. Well, if you look up to the top question, we worked out that the mass of hexane is 1.36. That's what makes this question quite hard. It's jumping in between the different steps and doing one part of a calculation, then going to another one, and then coming back to that. But number of moles, we know that N equals mass over RFM, or the mass over the molar mass. Our mass we worked out in the first part is 1.36. Our molar mass is 84. And so our number of moles is 0.01619 moles. And finally, you're asked to work out the molar enthalpy of bromination, and this is our last step, just as the same with the combustion calculations, just divide by the number of moles. Generally, it's of your fuel that you burn to get your water temperature to rise, but in this case, our fuel as such is of hexane. Okay, because the energy received is 1245 joules, but that's for 0.01619 moles of hexane. We want to now work it out per mole of hexane, so for 1 mole of hexane. How we do that is we take our enthalpy change that we calculated in this part of the question, the 1245, and we divide it by the number of moles. Okay, so our enthalpy value is 1245. Our number of moles is 0.01619. And that works out as 76,899.3. Think about your units. 1245 was in joules. This was in moles. So we've worked out our value in joules per mole. It's a very large value. So you're probably better converting it into kilojoules. How we do that is just divide by 1,000. And we get 76.90 kilojoules per mole. There's one more step to this though, and that's thinking about whether the reaction is exothermic or endothermic. And that's really important to remember because you need to include your sign with an enthalpy change, if it's positive or whether it's negative. And if we look up to this question about the temperature change, the initial temperature is 24.9, the final temperature is 32.1. So heat has been given out to the surroundings, i.e. the solution. If heat has been given out, the temperature of the solution has risen. That means it's exothermic, and exothermic is negative enthalpy change. So our answer is minus 76.9 kilojoules per mole. So check at the end. Is it exothermic or endothermic? If it's exothermic, you need to put a minus sign at the start of your answer. If it's endothermic, you need to put a plus sign at the end of your answer. And how you can tell that is by looking at the temperature change of your water or your solution. If the temperature goes up, that means heat has been released to the surroundings, and so it's exothermic. If the temperature goes down, then that means heat has been taken in from the surroundings, and therefore the surroundings have got colder, and that would make it an endothermic change. So while that's broken up into lots of steps and it's very complicated looking, it's always the same thing. Use your delta H equals MC delta T for whatever your solution is, be that water, be that this TCE solution. Use the values for that for M, C and delta T, all of your solution or water. And then divide by the number of moles of fuel or whatever you're adding in, the organic product. And then check your sign at the end. It's the same every single time. The last part of the question then is a bond enthalpy question. And it's using your answer from the previous part to work out a specific bond enthalpy of the CBr bond. And while usually you're given this data in tables, but you're given all the data you need in the question. And so what we have to remember is that the enthalpy change is always bonds broken minus bonds formed. So we need to have a look at the question and let them tell us what bonds are broken and what bonds are formed. So if we look at bonds broken first, and we'll maybe put them in green. So we're breaking a carbon-carbon double bond, which requires 612 kilojoules per mole of energy. And a bromine-bromine bond breaks, requiring 193 kilojoules. And that gives us a total of 805 kilojoules per mole. Then we want to look at the bonds formed. And again, they tell us in the question. We'll maybe do that in purple. So the bonds formed are a carbon single bond, which releases 348 kilojoules per mole of energy, and two CBr bonds. So that's going to be 2 times our CBr bond. And it works out, they don't give us that value, that's the value that they want us to work out. So now I can put that into my equation for delta H equals bonds broken minus bonds formed. And so I just sub in my values now. My delta H, I know from my previous question, is minus 76.9. Is equal to the bonds broken, which I worked out was 805, minus your bonds formed, which is equal to 348 plus 2 times my CBr bond. So all that's left to do is rearrange this equation and to find out what our CBr bond is. So just treat it like any normal algebra equation, rearranging, grouping your numbers together and making the CBr bond be the subject of your equation. So we're opening out this bracket here, it's minus, and then plus 348, that's minus 348, minus our 2 CBr bonds. Because our CBr bond is what we want to find out and it's negative on the right, we'll bring it over to the left hand side and bring all our numbers to the right hand side. So we've got 805 minus 348, and then bringing our minus 76.9 over, that becomes plus 76.9. And if you add all those numbers together, you get 533.9, but that's 2 times our CBr bond. So all we have to do is divide by 2 to find out what 1 CBr bond is, and that works out as plus 267.0. And then finally just add in your units, just as with all the other bond enthalpy values, your units are kilojoules per mole. So it's plus 267.0 kilojoules per mole.